This is a lesson on linear functions and intersecting linear functions and their graphs in a precalculus course. As I'm starting out here in precalculus, I assume that you've seen things in intermediate algebra and college algebra, especially regarding linear functions. This is a good walk into their Cartesian coordinate plane and graphing on x and y axes and locating points and writing equations of lines. So there's basic skills that I expect you to know at this point regarding lines that I'm not going to review. I do expect you also to be able to solve complicated linear equations by this point in the math curriculum. Graph a line using intercept and rise. Solve for intercepts, being able to solve for the x-intercept and the y-intercept. You should be able to do that. And you should be able to write an equation of line given a graph or points on that graph. So given this graph, I expect you to be able to write the equation of the line that this graph represents. Okay. You probably also moved into function notation with lines, and it shouldn't be a surprise to you that we're going to use function notation, the function of x. When we put the input x in, we're still going to retain the m and the b, the slope. You all remember that this is the slope of a line, and b is the y-intercept. So when we look at 0, b, that will be the y-intercept, and the slope gives us the rise over the run. And so I like to do the smart way of doing this. I'm not going to pick 2 points on here. I'm just going to do a rise over run, and that'll give me the slope of the line. And as we're working with average rate of change and different quotients, I'm anchoring what you know about the slope of a line to this newer concept of average rate of change and difference quotient. The slope of a line, m equals delta y over delta x, should be very familiar to you at this point in the context of lines. And what we're going to note is this equation here is what the average rate of change is. It's not interesting for a line. The average rate of change for a line is constant over the whole line, and that's basically the definition of a line. But as we move forward to more toolkit functions, and you've seen this a little bit in average rate of change, is that we can use lines on graphs that aren't linear to tell us things about average rate of change, and we're moving towards calculus and derivatives with this difference quotient and looking at slopes of tangent lines. All right, so looking at slopes and the relationship with slopes, and also this slopes increase or decrease. Do they have a positive slope or a negative slope? So when I look at this situation, which graphs represent negative slopes and which one represent positive slopes? Additionally, all of this you should be able to do with applications. So I put position versus time graphs over here with an anchoring in physics, position versus time. And would you be able to write an equation of a line given some time and position coordinates? I wanted to cover really quickly linear functions in their graph. An example here, so that we can brush up on some of these skills. F of x is a linear function, and we're given 2 points here. F of 6 is -5, and f of 10 is 4. Right away when I see that information, and as you're getting into function notation, you should be getting into this habit as well. The first, in these parentheses, that represents x. So I see 2 x values, and outside here equals, that's the y value. So I can write this down as 2 points, 6, -5, and also 10, 4. So part A, what is the slope? We're just going to do what we normally do, y2 minus y1 over x2 minus x1. And so order matters in math. I don't know if your teachers have enforced that before, but I will be checking for that. So y2 minus y1, so I'm going to take 4 minus a -5, x2 minus x1, 10 minus 6. And when I simplify this, I'll get -9. I'll get +9. I take the negative of a -5, and that gives us a +5. So 4 plus 5 divided by 4, 9/4. Okay, so that is the equation of the line. What is the y-intercept? Okay, we're not given the function of f of 0. We don't know what that is, but we know that will be the y-intercept. So what I need to do is, now I can write the general form of this function. I have mx plus b, right? Mx plus b, and I have the m value right now, so I know it's 9/4 x plus b. Well, we can do what we know to do in this situation to solve for the b value. We're going to plug in one of our points and look at the result. And that will allow us to solve for the b value. So I know f of x is 4 when I plug in 10 into the equation. So 9/4 times 10 plus b. Okay, so I have some simplification going on. 4 is 94ths, or if I do some simplification here, I'm going to get a 5 down in the bottom divided by 2. So that is going to give me 45 halves plus b. Now we're going to solve for b. So I'm going to say b equals 4 minus 45 halves. So I'm going to have to subtract off. I'm going to convert that 4 to halves, minus 45 halves. And I get b equals 45 minus 8 is 37 with a negative sign. 37 halves, negative 37 halves. So now that I have that b value, it says what is the y-intercept? We might say 0 comma negative 37 halves is the y-intercept. When we write out our equation for part C, I'm going to note that we're just writing out the equation. We did this over here. We started this over here. C. F of x is 9/4 x minus 37 halves. That's going to be our answer for C. Make sure you're using function notation when you do this. What is the x-intercept? The x-intercept happens when y equals 0. It's asking what value is x that results in y equals 0. So now that I have my equation, I can set my equation 9/4 x minus 37 halves equal to 0. And now I can solve for that x value that will tell me when the output is 0. Okay, so I get 9/4 x equals 37 halves. I'm going to multiply both sides by 4/9. 4/9. Right, that'll let us cancel. 37 is not going anywhere. I'm going to do this. I'm going to get rid of that 2. So 37 times 2 divided by 9. Whatever that value is, that's going to be the x-intercept, which will be 37 times 2 is, what is that, 74 divided by 9. That's about 8. I would say about 8 is going to be the x-intercept in there. So we might write it out as a point. 74 divided by 9, comma 0. That's the x-intercept. And then the y-intercept we already found out. Okay. So that was part D. Let's do this last part E here. What is f of 2? F of 2, I'm just going to take and plug into wherever I see x. I'm going to plug in 2. Minus 37 halves. This will give me what, 9 halves minus 37 halves, which f of 2 is going to give me negative 37 plus 9. What is that? Negative 28 halves, which is negative 14. So if I look at the point when x is 2, I should get an output of negative 14. Of course, I want you to check your graph on this. This is linear functions and their graphs, right? And their graphs. I expect you to be able to do all of this algebraically. I did not look at the graph at one point doing this, but I do want to show you the graph. And here's the graph of the x and y intercepts. You all see the x and y intercepts here. We have negative 18.5. And which I believe that's 37 divided by 2 is negative 18.5. And then also we have the 74/9. I said it's a little bit over 8, 74/9. That's our x-intercept. So that's our y-intercept and our x-intercept. We solve for those algebraically. And I want to look at the graph of 2. When x is 2, we got the output to be negative 14. I will draw the line x equals 2 on the graph here. That's what this is, x equals 2. I knew that was going to happen. The numbers from the back pop up here, and I'm not exactly sure why. So that's the line x equals 2. And what I'm going to notice if I follow that line to my function down here, I got that answer negative 14. You can see the negative 14 there. So now that we reviewed some basics on lines, I want to intersect them. Okay, so you know things about one line, but what I wanted to emphasize and review for the rest of this lecture is two lines. All right, so intersections and systems of linear equations. You've done this in your algebra classes before. You've solved algebraically for the intersection of two lines, and you've been able to use the graph to find that intersection point and read it off the graph. You've been able to write equations for lines given a graph and solve for that intersection. So given these two lines, can you write the equation for those two lines and then solve for that intersection point algebraically? And also doing this with word problems. You should be able to do this in a context with applications. We started intersection of lines with understanding the difference between parallel and perpendicular lines. Parallel lines have the same slope, so whatever the slope one line has, it's the same as for the other line. They have differing y-intercepts. Perpendicular lines have negative reciprocals for slopes, and perpendicular is negative 1 over the original slope. For example, if my original slope was 5/2, the parallel line will have a negative 5/2. I invert it and I take the negative of it. What I'm going to note is that the y-intercept is also different on here. I see students get lazy and they find that the negative reciprocal and then they just say they have the same y-intercept, but you have to solve for the new y-intercept. That original line and the new perpendicular line do not have the same y-intercept. We're looking at a problem. I'm preparing you for a problem here where you're finding the line parallel or perpendicular to another line with a point going through it. So you can see I identified a point here. All right. This point seems to be, each one of these is 2. So this point seems to be negative 6, comma, what is that? 12. Okay. And what they want to do, determine the equation of the line parallel or perpendicular to another. We're going to find the perpendicular line is what we're going to do. So that means we're going to need the slope of this original black line, and then we're going to determine like what is this y-intercept down here for a line that goes perpendicular to this original black line. All right, so when I look at the, I need to determine the slope of the original line. I'm just going to identify 2 points. I'm going to identify this point here, 0, 5. X equals 0, y equals 5. And I'm going to look for another one in here. It seems like maybe this point here, 3, 7. Yeah. So that gives us another point to be able to find the slope. Slope is a change in y over the change in x. So I can go 7 minus 5 over 3 minus 0, and that gives me 2/3. So the slope of that original black line is 2/3. It makes sense because it's positive, and it's not really steep. It's kind of less steep, so 2/3 seems reasonable. The slope of the perpendicular line is going to be the negative reciprocal of that, so that'll be negative 3/2. So if I want to find this line going through 6, 12, I know that it's going to have a form negative 3/2 x plus b. I need to solve for b still. Remember, I still need to solve for b. I can't just put 5 in. That line does not go through 5. So what I'm going to do is I'm going to plug in the point. That's why they give me a point. 12, the output has to equal negative 3 halves times 6 plus b. And you can note that the only thing I don't know in that equation right now is the b. So I can solve for b. This gives me negative 18 over 2, so I get 12 equals 9 plus b, and you can see that b equals 3. And when I look at the graph, that seems reasonable. I guess maybe my line was drawn a little weird. Maybe it's going through here, and then that would be a little bit more perpendicular. So the equation of that new line, I'm going to say, is f of x equals negative 3 halves x plus 3, and that would be my answer for a perpendicular line. As we move forward and looking at what if two lines aren't perpendicular or parallel, they're going to intersect, and lines, because they extend infinitely in each direction along a line, there's going to be exactly one solution. If you have two lines that have the same slope and the same y-intercept, that is the same line, and we're going to say that has infinite many solutions. If you have the same slope and two different y-intercepts, that is two different lines that will never intersect, and you have no solutions. So those last two are kind of, I think, uninteresting. There's not many they're nice for proofs, maybe, tests, but what happens a lot of times is we're interested in the one solution situation. So we're going to solve for that one solution, and we're actually you are responsible for knowing how to solve for it algebraically. And what we're going to do is we're going to take the equations of those two lines in the standard form here, the slope-intercept form. We have the slope-intercept form. And if they are crossing through the same point at the same x, then they will result in the same y. So we're going to set those two y values to equal to each other. Right? This y value is the same for both of them. Along this line, there's a y value. Along this line, there's a y value, and it corresponds to an x value. So we set those two equal to each other. We can solve for x and then solve for a y value if we needed to. And once we have this unique input solution, both lines, we can calculate that output. What I do want to emphasize is that you can always look at a graph. If you're not sure about your algebra, if your algebra is not working out to a correct solution, you can look at a graph. What I'm going to do for us right now is two things. Write an equation of the line containing negative 4, 2, and the point of intersection of these two lines. Okay, so there's two things going on. We have to create a line from 2 points, which we know how to do. We know how to do that. We've known how to do that since we took algebra. But we need to find an intersection of this line. So these aren't in slope-intercept form, are they? And I might say that's okay. You might feel the slide that I showed you just previously that you want to get them y equals. But what I'm going to do in this situation, because they're in this form, is to do the technique where you just add equations. 3x minus y equals 14. X minus 3y equals negative 6. I'm going to multiply this second equation by 3. Negative 3. And so then when I take 3x minus y equals 14, negative 3x plus 9y equals positive 18. Maybe you can see what's going on here. I get the 3 x's cancel. All right. I'm going to take this and do negative y plus 9y is 8y. And then I get 32 over on this side, don't I? So I get y equals 4. Once I know y equals 4, I can plug it back into one of these original equations. 3x minus 4 equals 14. Then I know 3x equals 18 and x equals 6. So the point of intersection, where it says the point of intersection of these two lines, the point of intersection of those two lines is going to be 6, 4. Remember, we have to do x, y. Even though we solve for y first, it goes in the second place. So that's the first part of this problem, is to find that intersecting point. And I can check with a graph too if I want to be able to just like know, did I get the right answer? There's those two lines. I graphed them and you can see that there's 6, comma 4. That's what we said our answer was, 6, comma 4. So now what we need to do, now that we have this point 6, comma 4, we need to create a line that also goes through negative 4. Let me find negative 4. These are all 2's, comma 2. Goes through that point. We need this line. This is the line that we actually want to find the equation for, through those 2 points. That's the line we're interested in. Of course, if we know 2 points on a line, we can find the slope. I did this in the previous example. Equals delta y over delta x. I have the point 6, comma 4 and negative 4, comma 2. I'm going to take the leftmost and the rightmost and subtract the leftmost. So 4 minus 2 over 6 minus negative 4, which is 2 over 10, which is 1/5. So the slope of that new line is 1/5. I know that the equation then is going to have a 1/5 in the spot where m goes, where the slope goes, but I still need to solve for the y-intercept. The y-intercept is in here. I'm going to plug in one of those points. That's all I have to do is to be able to solve is plug in one of those points. So when I plug in negative 4, I get 2 out. So 2 equals 1/5 times negative 4 plus b. Okay, so 2 equals negative 4/5 plus b. I add a 4/5 on both sides, so I get 4/5 plus 2. Well, that's 4/5 plus 10/5, and I get b to be 14/5. When I go ahead and write this equation, it says write the equation on the line containing that point and the intersection point. So this is the final answer. F of x equals 1/5 x plus 14/5. That will be the answer for that problem. Very satisfying. I think it's very satisfying as you improve your problem solving skills that you do two-step problems, that you're able to show 2 different techniques and combine them in an integrated way to find an answer. To me, that is a solid understanding of the material as you think about assessing yourself and how well you understand the material. I have a couple of word problems here, and they're not too difficult, but I wanted to show you a few word problems so that you have those under your belt as you're working forward in the lesson. There's a problem here. The age-old riddle is what I call this problem, where you have 2 people and they have different ages, and you have to figure out what their ages are. And we are in the situation of linear. What you're going to assume about this problem is that you're going to get 2 linear equations. So this is your general strategy. 2 linear equations, 2 linear functions, 2 linear equations, and you'll be able to solve for the intersection of those 2 equations. And what we have here is 2 different ages. So we're going to have an age on one axis, and we're going to have an age on another axis, and the age lines will intersect with one another. It's an interesting situation. So Leonardo is 4 years older than Natalie. So I'm not given any symbols, any variables in this problem, so I'm going to assign them. Let's let the age of Natalie be n. So that's age of Natalie. And no surprise here, I'm going to pick L for Leo, age of Leo. Okay. And this first statement gives me an equation. That is an equation. You can parse it into an equation. Leonardo, the age of Leonardo is, we know is an equal sign, 4 more than Natalie. So I'm going to take Natalie and add 4. And that is my first equation. Remember, I said my strategy is 2 linear equations. That's my first equation that I'm going to work with. Can you think of the second equation? What is the second equation? This is usually the hardest part of the problem. My hint is that in 6 years, the sum of their ages will be 66. So what we're going to do is we're going to add 6 to each of these. So we're going to have n plus 6 and L plus 6. And when I add those, when I have Natalie's age in 6 years and Leo's age in 6 years, when I add those two, I'm going to take Natalie plus 6 and add on Leo plus 6. When I add those 2 equations together, I get 66. When their 2 ages are added together, it equals 66. I'm going to simplify this. 6 and 6 is 12. So Natalie plus Leo is going to equal 66 minus 12, which I believe is 54. And this gives me the second equation to be able to solve. This one right here. I'm going to do a substitution method in order to solve. I'm going to take wherever L is in the other equation, I'm going to plug in n plus 4. So Natalie plus 4 equals 54. 2 times Natalie will equal 50, and Natalie's age is 25. That's how you do that. If Natalie's age is 25, that means Leo has to be 4 years older, right, than Natalie. 25 plus 4, which is 29. And it says, how old is Leo now? Leo is 29 years old. Okay, so algebraically, we solved it algebraically. Again, I think the hardest part about this problem is translating the information given in the problem to two equations that you can use to be able to solve. Of course, I have the graph for you. There it is. I mentioned that I have age on one side and age on the other. So there's the intersection point. I have Natalie, the x-axis, and Leo on the y-axis, and you can see that when at this point in time, she's 25 and he's 29. Translating words into equations is typically a very, very challenging task in math, and as you move forward into other sciences where it's the nature of word problems to assess the material in the course. One example I have is flying with a plane in the wind. Okay, a man flies a small airplane from Fargo to Bismarck, North Dakota, a distance of 180 miles. So I'm going to notice that 180 miles. I'm going to need that quantity, I assume, at some point. Because he is flying into a headwind, the trip takes him 2 hours. On the way back, the wind is still blowing at the same speed, so the return trip takes only 54 minutes. What is the plane's speed in still air, and how fast is the wind blowing? Okay, so I think there's a lot to parse out here, and I can understand that this is a difficult problem as you're approaching this material at this level. What I'm going to remind you is that distance is rate times time. Distance is rate times time. And I even changed this because I'm a physicist. I'm going to call it a velocity times time, a speed times time. So what I know is on the way there, on the first trip with the flying into the wind, all right, the person goes 180 miles, and there's a time of 2 hours, and there's some speed that they have, v1. And I'm going to note that v1 has to be a subtraction of the two speeds. The plane is trying to fly, but the wind is against it, right? So it seems like I need two different variables now. I need the velocity of the plane and the velocity of the wind. It says, what is the plane speed in still air? So it seems like I'm trying to find the velocity of the plane, but I have this wind term in here that I don't know. So on the way there, the velocity total that the plane can move is going to be that velocity of the plane in still air. All right, so this is in still air, and this is the wind. The velocity of the plane minus the velocity of the wind is not going to go as fast. As opposed to on the way there, it's going to get a tailwind. On the way back, the wind is still blowing, so the return trip is going to be faster. The plane is getting this boost from the wind here. Okay, so when I write out the equations that I'm looking for, and remember we're doing intersecting equations, intersecting linear equations. So your goal is to be able to get two equations you can solve for your input and output variables, right? You have two equations, two unknowns, and then you're golden. So in here, I'm going to put in the place of V1, I know it's going to be my two variables is going to be V plane minus V wind times 2. My second equation, that's on the way there. On the way back, I get the boost from the wind, so I have a plus in here, and then I was thinking about the number on the end. This is 2 hours, and they give me 54 minutes. I think part of this problem, the difficulty here, because I have 2 here, and I believe they want the speed of the plane in miles per hour, I'm going to convert that 54 minutes to hours. There's 60 minutes in 1 hour, and so that gives me 54 over 60, or a 9 over 10, right? If I divide by 6, 9/10. So 9/10 is 0.9 on the end there, the time. So I have a rate times a time equals a distance. What I'm going to note is both of these is equal to 180. What I might do is multiply stuff out or do a substitution. There's a couple of ways that you can move forward with the strategy. You can't just set this to equal because you have 2 variables. So I do believe you'll have to multiply them out. 2 velocity of the plane minus 2 velocity of the wind. 180 equals 0.9 the velocity of the plane plus 0.9 velocity of the wind. I'm going to go ahead and leave you to use your past skills on how to solve linear equations to figure out the rest of that problem. But that's the setup. I wanted to take a moment and just help you set up that problem.